All right, for this lesson, I wanted to focus specifically on this kinematics equation. Usually it's the third one on your list, but delta x equals b initial times t plus 1/2 at squared. And the main focus of this is, and obviously with this particular kinematics equation, when you don't have a b initial, when the initial velocity is 0, you can cancel this part of the expression out, and it's simply delta x equals 1/2 at squared. But in scenarios where you don't have access to the final velocity and you're solving for time, rearranging this particular formula can be kind of problematic, and it ends up becoming a quadratic formula. So real quick, I wanted to review what the quadratic formula looks like. I'm not going to go into all the nuts and bolts on this, but anytime you have this scenario where you have an ax squared plus bx plus c, remember your quadratic formula is going to be rearranged to equal to negative b plus or minus b squared minus 4ac over 2a. Like I said, this isn't a lesson on the quadratic formula, but it's more of a lesson just to be able to make sense in how this particular kinematics equation is going to rearrange to look like this. And then we'll do a quick sample problem when we're done. So let's look at this formula real quick. If we move delta x over, so if we move the change in displacement, and I know this may be symbolized with several different things, maybe a delta y, some physics books will use an s instead of x's and y's. And it just depends on which book that you're looking into. But we're going to say that delta x is the displacement. If we move that over, notice that it becomes negative. And that is probably the most challenging part of this. Some people have an easier time just going ahead and plugging in the number before moving it, before substituting into the quadratic formula, because it does change whatever your directional component of your displacement is, which you'll see in just a second, because the example I'm going to do will illustrate that. So anyway, if we look at the quadratic, or if we look at this kinematics equation, and we start substituting this in to the quadratic formula variables, you're going to notice that the 1/2 a, so 1/2 of the acceleration is equivalent to a in your quadratic formula. Okay, the v initial is b, and your delta x is c. Okay, so if we're solving for time, then time becomes this x variable here. Okay, so all of them are equivalent to one another. The big key here is that the 1/2 a has to stay together. Okay, so anytime that we sub this part into the quadratic formula for a, and notice this is going to happen twice, then we've got to take the 1/2 a both times. So let's go ahead and rewrite this expression to get our equation and what it's going to look like when we write it in quadratic formula. Okay, so t equals negative b, so negative b initial plus or minus square root of b initial squared minus 4 times 1/2 the acceleration. Now, some people would just go ahead and put a 2 times the acceleration in there because the 1/2 cancels the 4. That's fine. But we're just I'm going to write it all in right now. Excuse me, times negative your change in displacement. Okay, so it's real important here that we keep that negative in there for right now. We'll end up changing it to a positive here in just a second. It just depends on what your problem looks like. Okay, and this is going to be over 2 times, once again, 1/2 a, because this part of the expression has to go in there. Now, once again, we can go ahead and cancel this out. We can go ahead and change the 1/2 and change this to a 2 if we want to as well. Now, if you notice, this part of the expression here basically becomes one of our kinematics equations. Okay, so v final squared equals v initial squared plus 2ax. So all of it ends up tying in together. So what happens here is this particular formula is a combination or the derivation using two different kinematics equations anyway. Okay, so when we're solving for time, we could go the long route and just solve for 2 equations, or we can put it all together in one step and use the quadratic. Okay, so let's use this formula real quick to calculate this. We have a car moving at a velocity of negative 25 meters per second. Okay, so it just simply means that it's moving to the left at 25 meters per second. its initial position is 100 meters, and its final position is 0. And what we're looking for is the amount of time for this to occur. I guess I should give you the acceleration as well. This object is accelerating at a positive 0.5 meters per second squared. Okay, so here's what's happening. And like I said, sometimes you've got to really just look at the problem first so that you kind of understand exactly what's going on. We have an object that vehicle is moving to the left, but since the sign on the velocity is negative and the acceleration is positive, even though it has a positive acceleration, it's actually slowing down. Okay, so this is going to be moving from right to left, and it's slowing down as it's moving that, and we're looking for the amount of time for it to get to this 0 meter mark. Okay, so anyway, let's go ahead and solve for this. Oh, one more little thing about this problem. This is actually going to cross the 0 meter position twice. Okay, one time it's going to cross it as it's moving this direction to the left, and then eventually it's going to slow to a stop, and it's going to come back and eventually cross that position again. Okay, so now if you know enough about the quadratic formula, you get two possible answers here. So it should kind of make sense when we see our answers. Okay, so anyway, let's finish this problem out. Time equals negative the initial. I'm going to cut this down just a little bit so I don't run out of room. Okay, so I've got a negative times a negative here, so obviously that's going to make that positive. Plus or minus 25 meters per second, and I've got to square that. Now you can put the negative in there if you want to, but obviously a negative squared is going to make that a positive as well. Minus 4 times 1/2 times 0.5 meters per second squared times. Okay, now this is where it gets to be a little bit tricky. Okay, our displacement on this problem, delta x equals negative 100 meters. Okay, so we actually went from the positive 100 meter mark to the 0 mark, so our change in position was negative 100 meters. So if I put negative 100 meters in here, this is actually going to be written as a positive 100 meters. And I'm going to put this over 2 times 1/2 times 0.5 meters per second squared. These go away as well. Okay, so if I solve, and then one thing is really helpful if you solve this part of the expression first. Okay, so the next step of this is saying that time equals 25 meters per second plus or minus. And if we take this part of the expression and we solve for it ahead of time, we're going to get 22.9 meters per second when we solve for this. Okay, so let's go ahead and use that. I'm not sure how many sig figs I started with here, but we're going with 3 on it. So, and this is over 2 times 1/2, which we canceled out, so this is over 0.5 meters per second squared. Okay, and what this essentially becomes, another one of your kinematics equations is V final equals V initial plus AT. And if we rearrange that, we have time is V final minus V initial over A. Well, this becomes V initial plus or minus V final over A, and notice once again, we're going to get 2 particular times. At 2 time periods, this is going to be going at 22.9 meters per second. Once to the left, and then it's going to stop and come all the way back, and it's going to be moving back to the right again. So we're going to get 1 time for each of those. Okay? So if we solve for both times, we get one of them is 95.8 seconds, and our other time is 4.2 seconds. I would say we can use some common sense to figure out that for this car to move from here to here, it's going to take 4.2 seconds. And then it's going to keep on going, stop, come back, and it's going to cross that 0 meter mark again at the 95.8 second mark. Okay? Hope that helped.